Hello. You should hear me now and see the desktop. Does that seem okay?
Yes, Professor.
Okay, thanks. Okay, okay, gonna go through the rest of the code for language 7 today. Uh, what that means is, well, let me download it. We need to look at the details of, where is it? Of what the interpreter does for a function call. Okay, so we've done everything so far, but analyze a function call. So let me unzip this. Okay. All right. Okay. Um, let's see. Um, remember what we did? We analyzed. We were looking at this one program, and this program has this abstract syntax tree, and we looked at the part of the code that put the we looked at this part here that put this into the environment. Okay, what this thing does, it puts the variable f in the environment with the value pointing at that lambda. It's like a function pointer. It's just like C, except that what f does is it literally points to that branch of the tree. So this is really what's stored in the environment is a pointer to that branch of the tree. And what's stored here in the environment, this thing, I write it like this, but really what it is just it's a reference to that object. So it's a reference to that tree. So G's value is a reference to that tree, and F's value is a reference to that tree. So they're very much like C. C function names are literally the address in memory of where the code is. And here, a function name is a reference to the tree that holds the code. And I just write it here as if it was the tree was sitting there. But that's just what the pretty printer prints out. What's if you okay, if we look at the code, a value object, holds a tag. It could either be an integer value, a Boolean value, or a lambda value. And a lambda value is a reference to a tree. So what the value holds when it's a lambda object, it holds a reference to a tree. So that's represented here when f is a lambda object, this guy here really is a reference to this tree up here. And this thing here is really a reference to that tree. The pretty printer for the environment, when the environment prints, when the environment prints a value, the value two strings, yeah. Oh, that's it. The toString for a value looks like this. Okay. Now, but that toStrings, remember, toString is recursive. When you toString something, you're going to build a string and you add that tag to the string. But that means that you call toString on this guy. So when you get to here, you're calling toString on this. This is a reference to a tree. So that means you're calling toString on the tree. And if you look at what toString does on a tree, it just prints out the tree as a one line. It doesn't pretty print the tree. It prints the tree in one line. It prints the tree like that. So that's the result of toStringing a tree, which is the result of toStringing a value. Okay, actually, you should start getting used to thinking about Java this way. I have an environment object. Okay, so I have an environment class. The environment objects hold value objects. A value object points to a tree object. Okay, in the interpreter, when you get here to handle fun, remember we went through this the other day, the last thing it does is it prints out the environment. Okay, when you print the environment, you call toString on the environment. So there's toString on the environment. The environment steps through the table and it calls toString on every value. See, so it gets a value and calls toString on it. Okay. Okay. The values then toString themselves, but that toStrings this guy, so that calls toString on the tree. Okay, so when you print an environment, you call toString on the environment. ToString on the environment holds the values, so you call toString on the value. The value holds a reference to a tree, so you call toString on the tree. And you end up getting that output. You get an output that looks something like that. Okay. ToString the environment caused you to toString a value, which caused you to toString a tree. Okay. So we went from toStringing an environment to toStringing a value to toStringing a tree. And yeah, that's how you're supposed to think in Java. You have to imagine how these toStrings are all going to put together when you want to print something like an environment. When you want to print an environment, you have to imagine, well, printing an environment, it's going to be printing it's like a table, but the table holds values and the values point to trees. So you kind of have to think about it all at once. You have to think about all those toStrings, how they work together to give you an output you want. Okay, so this is what we did the other day. We did this part here, which puts these trees into the environment. Okay, so that's what it means to evaluate this guy here. Okay, now we want to evaluate the apply. We want to call the function. Okay, so we want to look at the code for calling the function. Okay, now here's how I'm going to do this. I took this function and I put it in a little file. Okay, so I put it in a little file I'm calling demo. Okay, I'll put this up on the website in a while, but I create a little file called demo. Okay, demo.language7 is there's a language 7 program. I want to run this program. Okay, so this is it's like writing if I want to run a Python program. Okay, what we're going to do is that's what this guy here does. This thing is the interpreter. Now, normally we've used it as a REPL. Okay, so you can use it as a REPL. Okay, or I can, so there I put a X, here I can put a function fun F, which is a lambda X times X. There's the squaring function. Oh, let's see, not one too many. There, okay, see, I just put that F into the environment with the tag is a lambda. So ignore that value, There's the lambda value, and then you toString, that really just toString this thing here. It's actually a tree. It's not printing that string. Remember, the parser built the abstract syntax tree. The value L points to the abstract syntax tree, and this is printing the abstract syntax tree. It's not copying that string. That string was parsed into an abstract syntax tree, and then I stored in the environment a reference to the abstract syntax tree. Then when I print the environment, I call toString on that reference in the environment in the tag, and that pretty prints the abstract syntax tree back that way. Okay, and yeah, if I, you can kind of see, like if I do this, like g of y is, yeah, I'll do this kind of funny. So, okay, I mean, okay, notice that it didn't read, what's printed here is not that string, because that string was parsed into an abstract syntax tree. And over here, the picture of the abstract syntax tree is right there. Okay. Every time you type in a command at this prompt, it draws you a picture of the abstract syntax tree of that command. So I typed fun g blah blah blah. So there's fun g. There's the abstract syntax tree. So this string was parsed into that abstract syntax tree. Then a reference to that abstract syntax tree is stored in the environment. And then when you pretty print the environment, when you print the environment, you two-string the environment, you two-string every entry in it. Eventually you get to two-stringing that abstract syntax tree. And then it prints out nicely like that. Okay. All right. So now what we want to do now is get to calling the function. Okay. What happens when I, like now I could say, whoops, I could over here, I could say apply f to 5. Okay. Well, what happened was I called f with value 5. Okay. Well, let's see. What I need to do is, I remember f in this, there's f. F is a lambda with one parameter x. Okay. When I called f, okay, there's the function call, apply f to 5. There's what f is. F is the function lambda x equals x squared. Okay. All right. So when I call this function, I have to look up this in the environment to get a reference to its lambda expression. So here, I'll just think about it in these pictures. You apply f to 5. You got to figure out what f is. So you have to look up in the environment for f in the environment. And you find out that f is a reference to this lambda. Okay, that's stored, see, that's stored here in the environment. F is a reference to that lambda. Okay, so you've got a pointer to that lambda. Okay, now you're supposed to call f with that parameter. Well, you look inside this lambda and you see that it takes in a parameter x. So that means x equals 5. Okay, now, what we need to do is we have to come up with a way of saying x is 5. And then down here, this is going to be 5 times 5. The way we do that to create x equal 5 is we create a new environment object. That's this function activation record over here, function activation environment. We create an environment with the variable x and the value 5. The variable comes from the lambda expression. The 5 comes from the function call. So I build an environment. Now this is, we'll look at the code in a minute, but you can see it's a little bit tricky because I'm evaluating this function call. To evaluate this function call, I need to create what we call a binding between the actual parameter and the formal parameter. The actual parameter comes from the function call. The formal parameter comes from the function definition. So I have to look in a couple places and build an environment that uses this variable with that value. So that down here, I create that environment that has the variable x and the value 5. Then I evaluate this expression in that new environment. Okay, so this expression is evaluated in the environment that holds x being 5. Okay, so you can kind of see, you can see it in pictures here that you're calling, you're evaluating this tree, but f is a reference to this tree. So apply has to look up f in the environment and get a pointer to this tree. Then when apply's got a pointer to this tree, it looks over here and says one parameter, and it looks over here and says one argument. Okay. Now, if I make a mistake, for example, if there are two parameters over here and only one argument over here, the interpreter is supposed to throw an exception and say that there's something wrong. There's not enough arguments for the function. Similarly, if there were two arguments over here and only one parameter over here, the interpreter can say, this is not a correct apply. There's too many parameters. Notice that would be the kind of thing that compiler usually does. Now it's going to be done by the interpreter. So when the apply looks up f in the environment and gets a reference to that lambda, it looks over here and says one argument. Looks over here and says one argument. Okay, things are all right. The apply and the lambda agree with each other. So then it says, okay, now I'm going to build an environment. I look up that variable in the lambda, that's what I put into the environment, and I look up that value in the apply and put that into the environment with that x. Okay, so you look in this tree for that, you look in this tree 0 branch, that's the variable to put in the environment. You look in this tree's right branch. Well, if there were more than one, we'll do it in a minute, we'll do a function call with more than one argument. So you actually have to walk this tree because there could be several parameters over here and several arguments over here. In this simple case, there's just one parameter here and one argument here. But you have to look in this tree for the name of the parameter. You have to look in this tree for the value of the argument, and you put that in a new environment. Okay. Then after you've created this environment, using that environment over here, you evaluate this part of the lambda. You evaluate that expression using the new environment. And then the evaluator, that's a recursive call on the evaluator. Remember, we're calling the evaluator on this apply, and that evaluator has to evaluate the body of the function, but it evaluates it in an environment that has the parameter bound to the argument. Okay, so evaluating apply means building an environment in which you can evaluate the lambda's body using the environment that binds the parameters to the arguments. Okay, and if you read this language 7 file here, it says all those words are explained in here too. Okay, so there are paragraphs in here where it explains the steps that the evaluator goes through to do a function call. Okay. See, like right here. No, I'm sorry. Here, starting here, applies the most complicated of the new syntactic form. So here's the paragraph that explains what apply does. So if you read that paragraph, it just spells out what I just said a minute ago. What does apply do? Well, apply, summarize again. Apply first looks up f in the environment to get its lambda. So apply looks up f, gets a pointer to the lambda. Then apply says, okay, now I've got a lambda. Now let me see how many parameters were in the lambda. How many arguments do I have over here? Do they agree in number? So they're the right number of arguments for the parameters. If there is, fine. If there isn't, throw an exception. If there's the right number of parameters and arguments, then we create a new environment, an activation environment, and we start binding arguments, parameters from the lambda with arguments from the apply. So we build the environment. After all now that's the parameter passing stage in like languages like C and C++. That's what you think of as parameter passing. You're passing the arguments to the parameters. What we mean by that is you're building an environment. Okay. In C, which is a compiled language, you do this by building a stack frame. This is what the C language would call building a stack frame. The stack frame holds for every argument for every parameter of the function, the stack frame holds an argument value. Okay, for every parameter of the function, the stack frame holds an argument value. In our case, for every parameter of the function, the activation record holds that parameter bound to the value of the argument. Okay, So after apply builds that new environment object, then it's ready to evaluate recursively the body of the lambda expression using the new environment. Okay. Then when that evaluation returns, then apply returns that value for the value of the apply. F applied to 5 is the result of evaluating this branch of the lambda in the environment that binds this x to that 5. Okay. Now let's look at the code that actually does that. Oh, and here I typed it into the interpreter. Now let me show you. I can also do it by clean up a little bit. Okay. Remember I said I have this code in the demo program. So I have my little demo program here. There's my little demo program. Oh, we'll just the demo program creates a global variable z. Then it creates a function. And here I'm doing something a little bit more elaborate. I want that function to reference the global variable. So the function f is x squared plus z. So see, it's x squared plus z, where z is that global variable. So over here, the function f of x equals x squared plus z. Okay, and z is a global variable. Z is this global variable here. So I've got a local variable and a global variable. Okay, and then down here I've got another function g. G makes a call to f. So g takes two parameters, a, b, and its definition is a plus f of b. Okay, so it makes use of both the parameters, but it passes one of those parameters to the other function. Okay, which also makes use of this global variable. So we're seeing a function calling a function. So here we've got a function that uses a global here we got a function that uses a global variable. We'll see why that's a good thing to think about. And here we've got a function calling a function. Okay, and then here's a call to f, and here's a call to g. Okay, so here's my little demo program. Okay, notice I can even put the parser in our language knows how to handle comments. I haven't really pointed it out, but if you look at the parser and the tokenizer, it actually knows how to deal with comment lines like that. Okay, it has comments built into it. If I go, you can see it. If I go to this guy, see nothing happened. Yeah, or there x5. Okay, no, the comments aren't part of the program. So you notice that this comment didn't even generate an output. And the second statement, see the comments not showing it, the comments are just dropped. They're parsed, they're tokenized and parsed, and the parser just drops them. Okay, so the language does allow comments, but they're just totally ignored. They get tokenized, and then the parser just skips over them. They don't become part of the part. They have no role to play in the parse tree. Okay, so the language allows comments. So you can create, let me clean it up again. Okay, so I can put comments in these little demo programs. Okay, so f, the important thing here is f refers to a global variable and g calls f. Now I can run the program this way. I can run my little baby program. I'll open a command window. Well, I can run it two ways. I can just take the demo program and drag and drop it on the CMD file. The trouble is it runs and goes away. Now there's the abstract syntax tree of it, but the output of the program disappeared with the program window. You know, when you do this drag and drop, you know, if you just take this demo program and drag and drop it here, it pops up a window, but then you see there was stuff in the window, then the window goes away. So the way you should really do it is open a command window here. And then in the command window, in the command window, call language 7.cmd and give it the name of the program you want to run on the command line, demo.language 7. Okay, so I want to run that file in my language. This is essentially my interpreter for the language, and it can accept program files. I don't have to run. See, this program runs the REPL if you just double click on it. But if you call it on the command line with an argument, it expects that argument to be a program file. So it opens it, parses it, and runs it. Okay, so there. Now it opened that file, parsed it, built that abstract syntax tree, then walked the abstract syntax tree and evaluated it. And here's the result of evaluating it. Okay, I mean the program, the interpreter first pretty prints the program in the infix notation, so it makes it a little bit easier to read. So the program lets z be 100, f of x is x squared plus z, g of ab is a plus f of b. Then it creates a variable. It doesn't use these variables. Creates a variable cat, which is 5. Creates a variable dog, which is true. Then it creates a variable r1 to hold the result of calling f of 4. Then it creates a variable r2 to hold the result of calling g12. Okay, all right. And you can trace through the program a little bit. Before we look at the code, let's just kind of trace through the program here. First, it's going to put z in the global environment. So we see that happen. Then f is put in the global environment by the fun. First you evaluate that var and put z in the global environment. Then you evaluate that fun. You evaluate that fun and put f in the global environment. Then you evaluate that fun and put g in the global environment. See, the global environment's growing. Okay. Then after you put a cat in the global environment, and then put dog in the global environment. So cat is put in the global environment, dog is put in the global environment. So we've gotten through these, now through these lines of code. Now comes the function calls. Okay. This was putting dog in the environment. See, this put cat in the environment, this put dog in the environment. Okay, now after putting dog in the environment, after putting dog in the environment, now it's time to call f. Okay, and then the result's going to be then we're going to put an R1 in the environment with the result of that function call. But before putting R1 in the environment, we call this function. Okay, now you can see it happened here. This is the function call. From here to here is the function call. Okay, what it did was, what this did is it looked up f in the environment and got a pointer to that lambda. Okay, so f was looked up in the environment. F was looked up in the environment and got a pointer to that lambda. Okay, then after it's got a pointer to that lambda, it looks in the apply and says, I got to put 4. I got to bind 4 to x in an environment. I'm calling f with parameter 4. I need to bind 4 to x. And that's this function activation environment here. Okay. Now notice it's chained to the global environment. See, the little arrow says activation record chained to global environment. That's because we know that the function, this function f makes a reference to the variable z. Z's in here. So when you evaluate the body of this function, x will be in that new local environment, but z is the global variable. Okay, so when we evaluate the lambda expression of the function, x is here, z is here. If we didn't have this activation record chained to the global environment, we would get an undeclared variable. We wouldn't find z. Notice it's important that this thing be chained to that guy there. Okay, so the activation record is chained to the global environment because, like in C, any function that refers to a variable that's not a parameter is referring to a global variable. That's a rule in C also. If a function accesses a variable that's not one of the parameters or a local variable, it's a global variable. Now, Java has a more elaborate system. When a function accesses a variable that's not a local variable or a parameter, the variable could be a static variable or it could be an instance variable. Java's a little bit more, and C++ would be the same. In C++, if a function accesses a variable that's not a local variable or parameter, well, depending on where the function's sitting, what we call the non-local reference could be a global variable, could be a static variable, it could be an instance variable. Kind of depends. You have to look at the context of where F was placed to know whether this would be called a non-local reference. In C, non-local references are global variables. In C++ and Java, Java doesn't have global variables. So in Java, non-local references are either instance variables or static variables, depending on the way the code was written. And in C++ does have global variables. So a non-local reference could be either a global variable, a static variable in a class, or an instance variable in an object. Okay, could be a global variable in the program, static variable in a class, or instance variable in an object. In Java, it's either a static variable in a class or an instance variable of an object. And in C, it's a global variable. That's the only thing it could be. In our language, non-local references are global variables. Okay. And we'll see in a minute that I'll give you an example that shows why that. Oh, that actually. Let me temporarily put another example here. Show you why that matters. Suppose I put a begin here. And in this begin, I say var z 100. Then I call f again. Okay. One of the key ideas here is f makes access to a non-local reference, which is a z. Should it be that z or should it be that z? Okay, see? Now, we know that f uses a z. Should it be my local z or that global z? The answer is that if you look at the code, If you look at the code up here, you say, but when I get to here, that z is this one. So that's what it should be. See, this is called lexical scoping. If you read the code, when you get to z in the code, the only z that makes any sense is that one. That's called lexical scoping. That's what C uses. But there are programming languages that take another point of view. When you call f and you need a z, the most recent z was that. So you use it. That's called dynamic scoping. Okay. In the world of programming, if you Google this, you'll find all kinds of articles written about the difference between lexical scoping and dynamic scoping. Okay, lexical and dynamic scope. You find all kinds of articles about this. Static and dynamic scoping. Modern languages never use dynamic scoping anymore. Dynamic scoping fell out of favor a long time ago. Okay. But there are a small number of languages that still use it. Dynamic scoping, it's dynamic. You say, I'm calling f. It has a non-local variable z. So I use the most recently declared z. So, but that depends on the dynamics of the program. So this f, the most recently declared z was the global one. In this called f, the most recently defined z was the global one. In this called f, the most recently defined z was this local one. So it's dynamic. It depends on the running of the program. So that's called dynamic scoping. The original version of Lisp used it. The Perl programming language used it, and I forget what other languages use dynamic scoping, but it's now fallen out of favor. Nobody thinks it's a good idea anymore. It makes programs really hard to analyze. It makes programs very bug prone because it can be very hard at runtime for you to figure out what's the most recently declared Z. It doesn't have to be this obvious. It doesn't have to be anywhere near that obvious. So trying to figure out at runtime what is the most recent Z can be really hard to figure out. So modern languages all use lexical scoping. This function is still that one there, so the Z is this one. The Z here is the one that makes sense lexically. So what you do is you basically say, go backwards up the program and find the first Z by going backwards up the code. That's what Z it is. Okay. If I put a begin statement inside here and declared a local variable Z, then when I went backwards here, I would, oh, here let me make this even more elaborate now. The sum of x squared with Z. Now let me put it, now I'm going to add three things in the sum. Okay, this code's a little bit hard to read, but what it's saying is the function takes in this parameter x, and what it returns is the sum of x squared, Z, a begin block, declares a local variable Z, then looks it up. But this Z is that Z. This Z is that Z. Because I created a local environment and I put Z in the local environment, then look Z up again right away in it. Just to show you that this Z here, now you go backwards and say, oh, it's that guy. That's lexical scope. You take this Z and you go backwards and you get, it's that guy. So in this function body, there's two Z's, a global Z and a local Z. So sometimes you use the local Z, sometimes you use the global Z, but you always use the same rule, lexical scoping. If you see a variable, you go backwards in the code to find out where it was declared. If you see a variable, you go backwards in the code to see where it was declared. Lexical scoping, okay? And as opposed to that more other thing, the dynamic scoping, which says, well, in dynamic scoping, this, like when you get down here, in using dynamic scoping, this Z would be that one, but this Z would still be that one, because that would be the most recent Z defined. So if this was a dynamically scoped language, this Z would still be that one, but this Z would be that one. Okay, so that would be, let me, actually I should pull, I don't want, oh, I know what to do. Pull this out here and save it as a file, demo2. So that's demo2. And this one's demo3. So save the examples as separate files. The programming language doesn't let you have multiple progs in a file. You can't, I didn't write it to allow you to put multiple programs in one file. No language lets you do that, really. I mean, remember, like Java lets you put multiple classes in a file, but only one of them can be public and only one of them can have a main method. You really can't have two programs in one file. Same with C. there's no way you can put two programs in one file. Now I could, I mean, it's logically considered kind of a dumb thing to do, but I mean, I could have written it so that the program, you would evaluate one program and then see if there's any more programs, but I don't think that's a good idea. So, here's little demo programs. Okay, okay. There's our basic one. Then this one, demonstrates one kind of. This one demonstrates the difference between lexical and, this one is where you have to worry about. Okay, well, that's a local Z. This one's the global Z. And then when you call F, do you use lexical scoping, which means F's going to use the global Z, or do you use dynamic scoping, which means F will actually use the most recently defined Z? Okay, so you have to worry about, are you going to use lexical or dynamic scope when you have both a global and a local Z? I mean, the language by default, now this language 7 can switch between these two. Turns out to be just one line of code. The difference between lexical scoping and dynamic scoping is trivial in the interpreter. In fact, historically, there's a cute story to this. Lisp was originally designed to be a dynamic scope language, but I said that wrong. It wasn't designed to be a dynamic scope language. Back in the 50s, when they were doing this, they didn't really understand what they were doing very well. They wrote an interpreter for the original Lisp, and they wrote it in kind of what they thought was the easiest way. And then they realized after the fact that they had done dynamic scoping, and they realized that wasn't very good. And the guy who invented Lisp said it was a bug in the language. He said that when he figured out what he had done, he really thought it should have been switched to this, but it was too late. The language was designed essentially to be dynamic scope. Eventually, they changed it. Eventually, the Lisp language switched to using lexical scope. But for many years, the Lisp language used dynamic scope, and the guy who invented the language said it was basically a mistake. They didn't realize what they were doing because it's such a subtle difference in the interpreter. We'll see. It's a subtle little difference in one line of code, which switches you from lexical scope to dynamic scope. And at the time, these words didn't even exist. They were inventing this stuff back then. And after they looked at it real carefully, they realized after looking at these examples that there was something going on, and they realized that they really should have been doing that, but they were in fact doing that. So they eventually changed the language. Many years later, they actually did convert the language officially to lexical scope, but it initially started out, well, actually what they did is they switched it so that at runtime you could choose between dynamic and lexical scope. So if you had old code that used dynamic scope, it could continue to use dynamic scope. But if you wanted to write new code using lexical scope, so the Lisp language actually had two scoping rules, lexical and dynamic, and because of backwards compatibility, they had to leave both of them in the language. That's how languages get cumbersome. They make mistakes and they fix the mistakes, but they have to keep the old mistakes in the language anyway. So you have a language with both the old mistakes and the new fixes of the mistakes. So Lisp ended up with both dynamic and lexical scope in it. Okay. So it's not much of a change in the interpreter to switch between these two scopes. Okay. Right. Now, okay, so we got the idea now. So we've got the idea of what we need to do. Okay, remember if we go back here, where we were was we got down to this apply. We're applying F to 4. Over here, that was this activation record. Okay, X is in the local environment. F needs Z, and Z's in the global environment. Like right now, in this case, there's only the one Z. Okay, there is only the one Z. So it's pretty reasonable that the F would use that Z. We'll look at the other example in a little while where there's going to be a global Z and a local Z, but F will still use the global Z. Okay, right. And then we know the interpreter after it's built that environment, then it evaluates that lambda expression there in this environment here. Okay, So it evaluates that lambda expression in this environment. X is 4, Z is 100. Okay, so it gets 4 squared plus 100. Okay, now notice that see, there's 4 squared plus 100. Then it puts, see, after the function returns, it returns 116. Then the result of that apply is assigned to R1 in the global environment. So R1 holds the result of the function call. Okay. Now we're going to call the next function. Now the next step in the tree, the last step in this case, was to call G. We're going to call G and assign this result to R2. Okay. Here's the activation record here. So what you do is you go over, you look up G in the environment, and you get a pointer to that lambda expression. G's got 2 parameters. This function call's got 2 arguments. So far, so good. 2 arguments, 2 parameters. So then the apply gets those arguments, gets those parameters, gets those arguments, and puts them in a activation record, a function activation environment. So A is 1, B is 2. So 1 got assigned to A, and 2 1 got assigned to A, and 2 got assigned to B in that activation record, in the function call. Okay. Then in that environment, okay, now there's something a little bit tricky going on. Remember, when you evaluate the body of G, you're going to call F. So in the process of evaluating the body of G, you're going to call F. So that's this. This is the call to F inside the body of G. Now, when you get down here and you call F inside of G, you do the same kind of thing. You look up F in the global environment and get its lambda expression. You see that this has got 1 parameter and this has got 1 parameter. Okay. Now, this is a little bit tricky. What's the value of that parameter? The value of that parameter is looked up in this environment. See? So in this environment, we look up B while we're building this environment. We find out that B is 2. So 2 is what we put into this environment as the parameter of the value for X. So there's a kind of elaborate dance going on in here. We're evaluating we're evaluating the body of this lambda expression in an environment. We get to another apply. The apply has to build another environment. In the process of building that environment, we look up B in that environment. Okay. And then we also have the global environment. So we now have 3 environments. We have the global environment, the activation of G, and we're building the activation of F. The activation of G, the activation of F. The activation of G is chained to the global environment, and the activation of F is chained to the global environment. Notice the activation of X, the activation of F is not chained to the activation of G. That would be a form of dynamic scoping. Okay, this activation record is not chained to G. Now, see, we're calling F inside of G. You might think that F's activation record was chained to G. And you might think that because in a language like C, the activation record for F would be pushed onto the stack right after the activation record for G. So the stack would be the global activation record with the activation record for G, then the activation record for F. Okay, F would be stacked on top of G. But this is not a stack. That doesn't work this way. Okay, so in fact, the stack in C's programming language, people really mostly misunderstand what the stack is. In the C programming language, when you have the activation record for F stacked on top of the activation record for G, stacked on top of the global environment, the activation records aren't thought of as ordered that way. They're not F's activation record followed by G's activation record followed by this global variable. They don't work that way. Because F uses the global environment. F's activation, the function called F, if you look at the code, the function called F makes no reference to G. Yeah, there's nothing in here that has anything to do with G. So at runtime, the activation record for F only refers to the global environment. It makes no reference to anything to do with G. So in C, when the activation record for F is pushed on the stack above the activation record for G, that's misleading. The activation record for F has nothing to do with the activation record for G. You're kind of skipping over it because the activation record for F goes from there to the global environment, like we did here. The activation record for F is chained to the global environment. In the language C, the activation record for G would sort of on the stack be in between here, but it wouldn't be that you went from F to G to global. You'd skip over G, go from F to global. And that's how the C language does it. Now the compiler takes care of that for you. So even though the compiler puts 3 activation records on the stack, when it's evaluating F, it skips over the G activation record, and the activation record for F skips over the G record and it looks in the global environment. That's all handled by the compiler. The stack is just a convenient way to keep track of when to allocate and deallocate these activation records. The purpose of the stack is not that they're ordered. The purpose of the stack is to keep track of when to allocate them and when to deallocate them. So the stack is serving a purpose that's a little bit different than what most people think it's doing. It's not keeping track of order in terms of evaluation. It's keeping track of order in terms of allocating and deallocating. That's all. It's only saying that before F is going to return before G returns because G called F. So F will return before G returns. So F's allocation record is going to be deleted before G's allocation record is deleted. Okay. In this case, they're going to be deleted by the garbage collector. These activation records will be deleted here by the garbage collector. Here, they're in the C language, they're allocated and deallocated by pushing them on the stack and popping them from the stack. So when you call F, you push this activation record on the stack, but it's still chained. It's pushed on the stack after G's activation record, but it's still chained to the global activation record. So the stack will look like this guy, then this guy, then and there'll be only one copy of the global one. It'll be this guy, then this guy, then this guy, but this one's actually chained up to that one. It skips over the G activation record in the stack, but the compiler is the one taking care of that idea. Okay, so here we see this activation record. Now, when we called F inside of G, okay, we created that activation record, and we go over here and we evaluate F. Okay, now F has, see, the value for F is 2. 2 was the value of the parameter B in this activation record here. So that 2 got copied from there to there. Then F was called. When you called F, its X is 2 and its Z is this guy. Okay, so it returned 104. So F, this call to F returned 104. Okay, and then that was added to A, which was what was A? A is 1. So the return value should be 105. See, there it is. See, there's the return value, the 105 there. That would be 2 squared plus 100 plus 1. Okay. Okay. Now, so we've gone through it in words and pictures. Now let's look at going through it in code. Let's actually look at the code that does this process. Now, one thing about the code, here we talked about a call to G that made a call to F. Okay, so while we were in the call to G, we thought of call to F. That's done by recursion. The interpreter doesn't know about this. When the interpreter evaluates the body of G, it just makes a recursive call to evaluate the body of G. It doesn't even know that when you evaluate the body of G, you're going to be making another call to apply. That's the beauty of recursion. When you evaluate the body of G, you just say recursively evaluate that plus. That's it. In the process of recursively evaluating that plus, you end up looking up A and you end up calling apply again. But that's just handled all by the recursion. Now we did it here. We saw the result of doing all of that. We said, well, when you called G, you created this environment. When you got down here to the call to F, you created this environment. So we watched those things happen, but inside the code, it's not that complicated. Inside the code to apply, it doesn't have to worry about what happens when apply calls apply. Here we see an apply calling an apply. Here we're seeing the call to G, the calling G leads to calling F. So we think about that. What does it mean? But the code doesn't. A call to G recursively evaluates that body. That's all it does. It doesn't care how elaborate that body is because that's handled by the recursion. That's the beauty of recursive recursive programming. Recursive programming, everyone thinks it's harder. It's not harder, it's easier because it lets you think about less. Once you get used to it, recursion is really about thinking about less, not thinking about more. Now, some recursions are harder than other recursions. Some recursions are trickier than others. This is a good example of simple recursion. This is actually a very beautiful example of how recursion can make things much easier to work with. From the point of view of recursion, when this function call evaluates that plus, I couldn't care less how complicated that plus is. I just call evaluate plus. And evaluate plus does its work of evaluating the left branch, evaluating the right branch recursively. It doesn't care how elaborate that right branch is because that right branch is just being done by another recursive call to evaluate. So the complexity is hidden by the recursion. The recursion, and this is a beautiful example of how recursion makes things easier. There are examples of recursion that are hard. Recursion is most of the time when it's used in real programming, it's used this way. Most of the time recursion is used this way, where it actually hides complexity. That was what it's really meant to do. Recursion is meant to hide complexity. There are cases where it doesn't hide complexity. And you've seen one good example of that. That's the pretty printer you're doing in your homework assignment. I give you the pretty printer because it's about as ugly a case of recursion as you can get. The pretty printer is a good example of recursion that's messy. This is an example of recursion that's beautiful. The pretty printer is an example of recursion that's messy. There's something about the pretty printer where the recursion actually is hard. It does not hide the complexity. Okay. And it's a tricky thing. Why does most recursion hide complexity, but some cases of conversion make you stare the complexity in its face? Well, I don't know if anybody's got a good answer to that. The pretty printer happens to be an example of a form of recursion that is very tricky. The recursion is not hiding the complexity from you. But this evaluator is one of the most famous examples of a recursion where the recursion is beautiful. It hides all the complexity. You want to evaluate a plus? Okay, all you do is recursively evaluate the left branch, recursively evaluate the right branch, add the two answers. How complicated is the left branch? Who cares? How complicated is the right branch? You don't care because all you have to do is say evaluate. We saw that in the interpreter. If we go and look at the evaluating of a plus, that was under evaluate arithmetic expressions, way down here. Here's evaluate expressions. Oh, that's equality expressions. Relational expressions. Here's arithmetic expressions. Yeah. There's evaluate the left branch. That's all. Just evaluate the left branch. Okay, that's the left side. Now, then you have now remember when you add, you could be it could be plus x, or it could be plus xy, or it could be plus xyz. So there needs to be a little code to ask how many branches there are. But notice that all the complexities in that recursive call. How complicated is the left branch of the sum? Who cares? How complicated is the left branch of the sum? Who cares? It's just handled by evaluate the left branch. See, this is the beautiful kind of recursion. Just recursively evaluate the left branch. Who cares how complicated it is? Then here we'll evaluate the right branch. See, there's the right branch. If the right branch is there, yeah, there may not be a right branch because you can write plus x, and that just means the positive, or you can just write negative x, which is just a negative operator, or you can write plus xy. Okay, so, but again, you don't care how elaborate that branch is, you just recursively evaluate the right branch. That's beautiful recursion. Then that means the same time that I don't care that there's a function call inside of a function call. Now, in reality, it does create this complexity. I mean, I do need to understand how that's working, because there's the recursion. I just kind of oversimplified things a tiny bit. When you say evaluate recursively, I ignored something. I ignored that guy. And it turned out that was the thing that tripped them up with lexical versus dynamic scoping. They thought it was straightforward. Evaluate recursively the left branch, or in this case, the right branch. Evaluate recursively the left branch. Who cares how complicated it is? Blah, blah, blah. But there's a little trick. What environment are you going to use? Well, that mattered. And it turned out that environment, by not being careful with that environment, they were sometimes using lexical scoping and sometimes using dynamic scoping. When this function called that function, and you evaluated this right branch in the plus, it did matter what environment you evaluated this guy in. So there was a hidden complexity in the recursion. Recursively evaluate the left branch. Fine, that's the easy part. What environment do I use? If you're not careful, you screw things up. Or if you're not careful, you don't realize that there's an extra little subtlety to the recursion. The recursion is being done relative to that environment. That's where you look up the variables. So if you're not careful, when you have multiple environments, like in a function call, see, in a function call, there are multiple environments. There's the global environment, the environment of G, and the environment we're building of F. There's 3 environments. If you're not careful, you can use the wrong environment. Okay, so the recursion is beautiful. How do I evaluate the body? I just recursively called evaluate. But I do need to be very careful about what environment I'm using, because I do have multiple environments at that point. I've got the global, you can see them right there. There's the global environment, there's the activation record of G, and there's the activation record of the thing I'm building. I have to know which environment I should make use of. And that's where a lot of the thought goes into designing these interpreters. That you have to know the rules for which environment to use in which situation. If you use the wrong environment, well, you can switch between dynamic scoping and lexical scoping. Or worst case, if in one place in your interpreter using one notion of environment, another place in your interpreter using another notion of environment, you could be doing something really subtle, like some parts of your language use dynamic scope and some parts of your language use lexical scope. And believe me, that's happened. In the history of programming languages, things have gotten mucked up like that. There have actually been cases where people JavaScript is a good example. They just kind of mucked up how they were designing, how they were using environments. It was not really well designed. You could end up with really screwed up sense of, evaluate recursively But if you don't pay attention to this guy here, you can end up with really strange bugs or quirks to your language. Sometimes you're evaluating using one environment. Some other parts of the language do evaluations relative to some other environment. You don't have consistent rules about the environment. Okay. So the modern consistent rule is lexical scoping, but then you have to know how to handle the environments to do proper lexical scoping. So modern programming languages use lexical scoping for the environments, but then you still have to ask, what does that mean? How do I create environments that are properly lexically scoped? So the recursion is nice. It really, it's a beautiful form of recursion. I don't have to worry about how complex this expression is. I just evaluate it recursively, but I do need to worry about the environment. Okay, I need to pay a little bit of attention to what environment I'm using. Otherwise, I could get possibly inconsistent results. Okay, now over here in the evaluator, let's look up apply. Okay, there's evaluate apply. Okay, okay, so this is the thing that's going to this is what evaluates an apply branch in an abstract syntax tree. Okay, now roughly, real quick, apply needs to look up G, get its lambda expression. Then it needs to check that the lambda expression has the same number of parameters as I have arguments. After it's verified that there's the right number of arguments, then it creates an empty environment and starts binding A to 1, B to 2, okay? All right. Then after it's bound all the arguments to the parameters, then in the new environment, it evaluates the body of the lambda. That's it. Those are the steps. Okay. Step 1, look up G. Step 2, check the number of arguments. Step 3, create a new environment, empty. Step 4, bind the arguments to the parameters in that new environment. Step 5, evaluate the body of the lambda expression in the new environment. Okay, so go over here and we'll see those steps in the code. Okay. Okay, so first step, let's see. Now, I oversimplified this a little bit. Remember, okay, I said look up G in the environment. Well, that's because I'm trivially doing a named function call. But remember in class yesterday, we talked about, let me go back to the lecture from last time. We did these weird examples. Remember, you could apply the result of an if expression to an argument. Remember, see, apply applies something that returns a function. So apply is a little bit more complicated. See, it has to say, well, this thing should evaluate to a function. The simplest case is what we're doing. Over here, we're doing the real simple case, apply a named function. That's actually the most trivial case, apply a named function. But there are these much more elaborate cases that the evaluator needs to worry about. So like down here, we did some other examples. We did here. What that means is you apply the function A to the argument B, and you should get back a new function. So this should return a function that you apply the return value of this guy to that. Okay, so what the interpreter really needs to do is it needs to evaluate the left branch of apply to a lambda expression. It's not as simple as just looking up the name in the environment. In the more elaborate case, you have to evaluate this guy to a lambda expression. So if you look at the evaluator code, the first step is actually something a little bit more abstract. The first step is evaluate applies first parameter to a function value. Okay, so you evaluate the left branch of the tree. Now that could be as simple as get the value of this name, but notice you're doing it recursively. You're just saying, well, okay, there's a left branch, it needs to evaluate to a function. So recursively evaluate the left branch. But then you have to do a runtime check to make sure that what you got back was a function. Okay, so that's step one. Okay, evaluate the left branch to a function and make sure it really is a function. Okay, okay, if it is a function, then we have a pointer to its, if we get back a function, we get a pointer, we grab the pointer to its lambda expression. So if we look up G and it's really a lambda, then we store, I'm going to call it the variable lambda is a pointer to the function's lambda expression. Okay, now here's the check that the number of arguments, check that the number of actual parameters is equal to the number of formal parameters. That's just this check here. Okay, here's create the new environment. Okay, I didn't number, I think I'll renumber these. I'm kind of like, this should be a step in its own sense. Get the lambda expression, check that it's got the right number of arguments, create the empty environment. Okay, now this is the step here that loops on the arguments and the parameters. So now you have to have a loop that loops on how many arguments there are here and binds them to how many parameters there are over here. So that's a loop that does the binding in this environment of the actual parameters to the local environment parameters. Okay. Each local parameter, now notice that here I'm calling G with constants, but they don't have to be called with constants. Remember here, like here I called F with a parameter. So you had to look up that parameter. So each argument has to be recursively evaluated. So that's this part 4. Each argument needs to be recursively evaluated. Now we run out of time. We're going to quit here. Every time I call an evaluator, I got to be very careful about what environment I should be using. Because notice I've got a local environment here, and I've got the environment that the function was called with. I've got 2 environments already. I need to keep track of which environment I should be using. And that's one of the things we'll talk about. Every time you recursively evaluate something, the recursion's your friend, the recursion hides complexity, but you do need to worry about what environment you should be using. Like later on, we will call the evaluator with a different environment. See, there's an example of calling the evaluator with a different environment. Most of the time we'll use this environment, but every once in a while we'll use some other environment. Okay, so we'll quit there, and this is where we'll pick up. Okay? We'll go through these steps of, we'll finish talking about these steps. We've sketched them out in terms of these pictures. We've sketched them out in terms of these pictures and watching the code over here, but we want to watch the code do it. So we've watched the program do it. We've watched the interpreter do it, but we want to step through the code and see the code do it. The single most important thing, though, is kind of like, recursion is your friend, but you do need to worry about what environment to use. And that's one of the subtleties, is that if you use the wrong environment, you could either break the language or just make the language not be what you think it is. Like, the language doesn't really do what you think it should be doing if you happen to use the wrong environment when you recursively evaluate an expression. Okay, so we'll go ahead and quit there, run out of time. So on Monday, we'll finish this. And actually, oh, I forget where it is. We'll compare dynamic scope to local scope, to lexical scope. there's one change you can make in this program that'll actually change you from local scope, from dynamic scope to lexical scope, from lexical scope to dynamic scope. So we'll see that you can actually change the scoping rule of the language. Okay. All right. So we'll go ahead and quit there. That's what, and so we'll finish this on Monday, and then we'll be ready for the next language, which brings us into the world of real functional programming. Okay. Any question? Any last question? Okay. This stuff is tricky. Yeah, your book is this code. Yeah, this description of it. So this description along with the code, yeah, as grad students, you're ready now to get where somebody can just tell you, read the code. You know, if you want to know how something works, now you're to the point where the answer is read the code. Okay, that's what this is about. The answer to everything is read the code. So you should be reading this like it was a textbook. You know, read the code, really read the code, because that's how you can understand this stuff. You know, the code really is the final answer to how this stuff works. Okay, I'll quit there and have a nice weekend. See you on Monday. Bye.
Thank you.
Bye.
Bye.
Bye.